So generally in circuit analysis, it's very important that we're able to find the effective resistance. So if you see a circuit like this, because per what we've done so far, we could see clearly that these two are in a parallel, right? And then these two here are in series, right? But then what if you make something of this sort, right? You can't see clearly that these two are parallel, neither can you see these two are parallel, right? Neither can you see these two are in series. You can't even say these ones are in series, okay? So that's where what we call the star delta transformation comes in. It helps you to transform between two. So this is what we have. If we see something of this sort, something like this, we call it delta. If you see something of this sort, we call it star. But then again, these two are just a general outline, right? You can even, for this one like this, you can even see it as a T at times. So it could appear like this or even like this, right? It's still a star, right? So you just have to get the basic diagram in head, and then whichever way that it appears, you should be able to identify whether it's star or delta. Okay, but for these two or the configuration of resistors, there are relationship between them, and that's what we are going to do for today. And then we'll try and solve an example later to see how these help us to make the analysis of circuits easier. Okay. So what the whole transformation is saying is that you can transform delta to star or star to delta, right? But then one thing we should have in mind is that these two are related this way. I'm going to intersect the diagram so we see clearly what's happening. Okay. And then we are not going to derive the equations here, but we are just going to see how to identify the equations, right? Because at times the formula sheet is given, and then you have to be able to identify which formula fits where and which one fits there. Okay, so here it's just about understanding the concept and see how we can apply them. So now you can see that the star which we had here is actually within the delta now. Okay, so what the whole transformation is saying is that if you are trying to find, let's say, the resistor R1, right? Okay, so now let's do from delta to star first. Okay, so from the diagram you can clearly see that the star is within the delta. So one conversion you can keep in here to make your solving easier is that the delta, let's see, not necessarily in anything, but the whole transformation says that if you're able to transform, there should be equivalent, right? So let's see. So, but if you keep this, how we are doing it in mind, you'll be able to identify the formulas very easy. So keep it in mind that the star is within the delta. So somehow we keep a small conversion ahead that the delta is greater than the star. So it makes the formula identification. So we are trying to do delta to star, right? Delta to star, right? So which star elements will we try to find first? Let's see, RE, right? So RE. RE is the first star element you are trying to find, right? So whenever you are trying to find star from delta, meaning you are actually using the resistors from the delta, right? So if you are trying to find, so the deltas are R1, R2, R3, right? And the stars is where we have RE, RB, and then RC here, right? Okay. So if now we are trying to find RE, which is from the star, right? We are converting the delta to a star. That's what we do. When you look at the RE here, right? Let me find out. When you look at the RE, what are the resistors in the delta, right? That are just on the size of the RE, right? So you have basically a R2, R3, right? R2, R3. So what we do is that we do a product there, R2 times R3, right? And then on the denominator, we just add all the resistors in the delta. So that basically that will be R1 plus R2 plus R3, right? That's what we're saying for the delta transformation. We are not deriving formulas we said earlier. We're just trying to see how we can understand some basics within the formula, some tips and within the formula so to make your identification of the formula is easy. Because most of the times they're given the formula sheet. Okay, yeah. So try this if you're able to do it, but if not, let's do it. So let's see, if we're trying to find the next resistor in the star, which is about RB, right? Look at RB, what do? We know that clearly the denominator is just the sum of all the resistors in the delta, right? Which is R1 plus R2 That's R3, right? And then you have to first find RB and look at the resistors in the delta that are on the sides of the RB, which is basically R1, right, and R3. So that's how it's done. Okay, and now if you are trying to, so when you get the time, you can try the RC on own and see if you get it, but we'll come back and do it. So now the aim is now to convert from what? From star to delta, right? And initially, when we started, we were good to know that the star was on, the star was here, but I moved it to here. And then what we said was that the star is within the delta. So we made some kind of assumptions that the delta is smaller than the star, right? Sorry, the star is smaller than the delta. So that's how we go about it. So looking at this formula, because all this here, everything that we see right here is like we've converted, making sure that we get a star. So look at the what we get for the delta. You actually could clearly see something that the delta value should be bigger, right? So let's see somehow. So if you are trying to find, let's see, the first delta value, let's see, if you're trying to find right now is the first one, let's say R1, right? Which is this R1, right? Okay. So what this one says, when you're trying to convert from star to delta is that, let's say you're finding R1, okay? So we have adding two things up here. We have a limiter here. Okay. When you look at the R1, right? When you look at the R1, what are the resistors? That's are kind of directly opposite. Like you can see that they are kind of like connected to the R1. Clearly, it is basically the RC and then RB, right? So what the star to delta says is that you add those ones, right? That's RC, RB, right? Basically, we have RC plus RB, right? And then here, for these two ones here, you bring them down and you add them up. So sorry, for this RB and RC, you just find their product here. So basically, you have RB and RC, right? And the down will be the only one that is what you kind of like perpendicular to the R1, because our aim is to find R1 right now. And looking at this one here, the one perpendicular to the R1 is basically the RC, right? Sorry, RE, this basically this RE here, right? So you write that one here. It's just one element. So RE. Okay. So looking at this one here, this RE here, which is from delta to star, and then looking at this R1 here, which is from star to delta. Somehow, as we were seeing that the star is in the delta, so we kind of make some tiny, like funny assumption that the delta is bigger than the star. So looking at this one here is a delta, right? So you see this one, we have an RC, RB, right? So on their own, they are free, right? So how the delta is, so if you have the star, for instance, like this, right? It's not free. When we do it this way, the star is in the delta. So all these ones here are not free. So you see, they are kind of like related. But when it comes to delta here, the delta is free on its own, right? So that's why we have this, and then this on E. So when you have this in mind, identification of the formula is quite easy. So now that we've seen this, we're going to try an example to see how this actually helps us, right? So we identify that when we're starting that when you have something like this, it is not clear to see that you have the resistors to be in parallel or to be in series, right? So now we're going to look at this example to see how this actually helps us. Okay. So now the question wants us to find the voltage across just the 6, right? So you can't see clearly that, as we were saying earlier, that these two are parallel, right? And you can't see these two are series, right? So looking at it very well, are you able to identify a star on a delta or a delta anywhere within this parallel circuit? So as we were saying earlier, that what we said was, it's not always that you see the delta to be this way straightforward like this. It's not always that you see the star to be this way straightforward. The star even itself can be something like a T, right? So now go again. Yeah, I think by now you should identify. So clearly you can see that this one here is a T configuration, like, or a star conjugation of the resistors, right? So one thing we can do is that we could transform this to a delta to see if it makes our work easier. So then again, I'm drawing it, doesn't mean it should be straight, as I was saying. So this one could be turned to something like this, right? And we have something like this here, right? So redrawing this, let's see if we can clean this up. Okay, so let's just clean without clearing the values, and then let's transform it, right? Let's bring it back. So now we are just going to do the calculations and see what we get for this, right? And then there's something else for us to be able to identify. A minute. Okay. All right. So what are we doing here? Basically, the circuit itself has a what? A star. And we are trying to convert from star to delta. So I'm going to write the formulas out, and what we've done so far, think through and see which one is the formula that will help us. So let's see. So I'm just going to use letters, but here we're not using letters. So let's see. Let's do something like this. This is just an example though. RE is equal to, let's see, R1 is equal to RE plus RB, right? And then we have RE plus RE, RB, all on what, let's see, RC, right? And then we have something of this sort. Let's see, RE being equal to R1 plus R2 plus R3, right? And then for the top side, we'll get, let's see, R1, let's see, R2, and then R3, right? So this is just an example. We've not labeled the circuit here, so we can't say this one is R1, R2, or RA, RB, or something, right? So which formula are we using? So if we've been able to follow so far, it is clear that since we are trying to convert from a star to a delta, we know that, remember this, that if we have a delta of this sort, this is just to be able to identify the formulas. We know that the star is in the delta. So if we are trying to convert from a star to a delta, meaning that we should get a formula that gives us some kind of a bigger value, right? So clearly this one is what will kind of like give us a bigger value, right? So meaning that's the formula that we are using. So we clear this out, and now we give the representatives, right? So our aim right now is to find which one first. So let's see if we try to find the this one here first. Let's say this is RE, right? So meaning that if we are trying to find this RE, if this are RE, meaning that the one we're trying to find first, let's do the labeling. Let's make this about R1, right? And this one about R2, right? And this one about R3, right? So if you're trying to find R1, which is the one that will be on the brown line that we just drawn, okay, and then this delta, we use what? We use element from the star. And how do we go about that? What we said was that the RA and RB here will be the ones that are kind of like very close to the R1, which is the 2 and 2. So basically we have 2 here, and then we have a 2 here, right? Which are these 2 here, 2 ohms, 2 ohms, right? And then these 2 ohms appear here again, 2 times 2. And the one that's perpendicular to the R1 is what, this 2 ohms here. So this is how it to be for us to get our R1. Let's see. That's 2 plus 2 plus 2. And that gives us what, 6. So basically we have 6 ohms here, right? Okay, so if we are trying to find our R2, which is this one right here, which ones are closest to that? We have what? So let's see a minute. Okay, so if we are trying to find the R2, the one which is this, the one that we'll use is basically this one here and this one here, and they're also 2 2, right? So what I'm getting is 2 plus 2 plus, and then the product of these two, right? And the other one, which is directly opposite to the R2, which is this one here, right? Which is 2, right? And as we do this calculation, we get to see a very clear relationship here. Yeah, we will see it, and then we discuss it and then move on. This again gives us what? A 6, right? 6 ohms, right? And then the R3, the same procedure, right? Where's R3? A minute. Okay. So our R3, which is this, the ones closest to R3 is this 2 and 2, right? So we add them up and we get, well, 2 plus 2, and then we do their product here, 2 times 2, and then the other one directly opposite to the R3, which is this one here, like perpendicular, kind of like perpendicular to it, it's still R2, so R2 here, and then again that gives us what, a 6 ohms, right? Yeah. So we have 6, 6, 6. So now that we have all these, we can clean this delta within, sorry, the star within, and leave behind the delta that we just transformed to. Okay. So we have this. Let's put the resistors in. Okay, the resistors are in, and now we know this is what, 6 ohms, this is what, 6 ohms, and this is what, 6 ohms again for the R2. All right. So now that we have this, we could see some relationship and make the circuit easier, even easier to form, to be able to find the voltage across the 6 ohms at the terminals A and B that we are trying to find. Okay, so we redraw this. I think we should. Okay. Let's do this. But then we could clearly see that after we did all the computations, the delta resistors that we are getting are all what, the same, 666, right? And then that's because the resistors on the star were all what, the same value, which is about 2, right? 2. Okay. Okay. So as we redraw this, I'll be talking about that one. What we saw is that we had all the resistors in the star to be, all the resistors in the star, right, to be 2, right? And then when we started, we said something that we made some kind of assumption that the stars are within the delta, right? And then we said something like the stars are smaller than the delta, right? Okay. And then when we did this computation, we saw that the, what's the name, the stars, the resistors on it was 2 amperes, 2 ohms, right? And now after we did the computation, we get to see that the resistors in the delta are 6 ohms, right? Which is about 3 times, right? 3 times. What we can see about this is that when you're having a star configuration, right, something like this, and then all the resistors are the same, right? So let's do something else. Let's just do 2, 2, 2, right? And then you're trying to find a delta configuration, right? Because the values are the same, the ones from the delta configuration will just be 3 times this. So this times 3, that gives us 6. This 6 and 6 here. So if it happens that you get something of this sort, all of them, not even 2, it shouldn't be 2, all of them should be the same value. So let's say if you have something like, let's say 4, 4, and then 4 here, if we try to get the delta configuration, right, what should happen is that it should be 4 times 3. So here will be 12 ohms, 12 ohms. Here will be 12 ohms again, and this side will be 12 ohms, right? So that's what it means. This general observation, and then it works when you use it. So now that we've transformed this circuit, like we've redrawn it to make it clearer, we are going to do the computations, right, to see if we can get the voltage across the 6 ohms resistor. Okay, so now you could clearly see that right now it's clear that some of the elements are in series, some are in parallel. So now we're going to go through. So as we've done so far, you could move across these ones. You could move across this without passing through any element aside the 2 of them, right? So here it's supposed to be 6. So you could clearly see that these 2 here are in parallel, right? And then for these 2 again, you can move across these ones here without passing through any other element. So it's clear that these 2 are parallel, right? So if we try to find the effective resistance, this is how it will be. So let's try and redraw it. So we have our 10 volts here, so 10 volts here, and then we convert this to parallel, so we get about 6 in parallel with another 6, right? So let's just do it this way, kind of like a resistor, right? And then here we get what, a 6 which is in parallel with another 6, right? So we converted this one to 1, right? And then So 6 and then you can see that this one here, this 6 here is parallel with the voltage, so it should be something like this, where you get this and then a 6 ohms here. So this is ohms as well, and this is ohms. Okay, so this is the circuit simplified, and we could see the elements, the resistors very clear. That so this one here parallel, right? But then they are connected to this two parallel here, so that's why I've done it this way. But then this one here, this 6 here is parallel to the voltage. So now that we've simplified the circuit and then we have this, we can let's clean it up and then make it easier to see what we are doing. Okay, so now we simplified it. We've seen which ones are in series, which ones are in parallel, right? But then now we are going to just allocate the direction of current, and then the values that can be simplified, we simplify them. So now let's see. Minutes. Just clean it up to make it visible. So now this one's 6 parallel to 6. Let's simplify that one. Let's go back to a sum. Let's see, 6 plus 6, right? That gives us 3. So basically we have 3 ohms here, and then here to have 3 ohms. Okay, so there are two ways to do this. Either you do a current division or voltage division. But now let's see if we can do a current division, right? So first of all, we are trying to find the current, so let's choose a loop. If we choose this loop, you can try another loop later, but whatever it is that you choose should work, right? So if we choose this loop and then we are doing and we go by, okay, okay, so we could clearly see that if we put the voltage on one side, right, and we put the resistors on one side, the current flowing through this side will be, let's say, 10 and 6, right? And that gives us 5.3 amperes, right? So that's the current flowing through the side, right? So that current will be flowing through the side, 10.6. So let's make that I. Right? But then if it gets here, there's a chance it will actually split between these two. But if we choose that loop, we find that I. But if we choose this one, it will split to this. Let's make this one I1 and this one right here I2, right? So current division. And when we're able to find the current, we're able to find what's happening to this 3. And when we're able to find what happens to this 3, we're able to find what's happening to this 6. That is our initial interest, right? So this is how we do it. To find I1, let's see I1, right? Because I1 is the one going to what we are looking for. So I1, right? Let's clean this up. Okay. So I1, right? So definitely we can see that we could add these two up and we get just one resistor, which is about 6 ohms, right? So if we want to find the current flowing through that one, this will happen. We do this is the opposite one, so 6 all on 6 plus 6 times this 500. It should be 6 on 6 plus 6 times 5 on 3, right? Yeah, so as I was saying, this should be about half, so that's 5 on 6 ohms, right? Half because the resistor here is 6 ohms, this one's in series, so 6 ohms, so the current will split equally, right? So 5 on 6 ohms. Okay, so now that we have this, but our aim was to find the voltage, right, across this 6 ohms here, which is now in this one, right? So if we have the current, we can find the voltage, right? The voltage that we are looking for, IR, right? And then our current is this one here, this 5 on 6, right? So 5 on 6, and then our R of interest is just 6 ohms here. That gives us 6, right? So that ends up giving us 5 volts, right? But then there's another way to do it. This we're using current division and it looks a bit long. So this is how we can do it. let's clean this up and see how we can go about it. Oh, that's messy. So let's clean this up. Okay. So basically, we have a version of the current division which we see voltage division. Okay. So clearly, we can see that the 10 volts here and this 6 ohms here are parallel, right? So definitely, this whole voltage, the voltage across this one will be 6, right? Okay. But then this 10 volt here is also parallel with this branch here, right? So definitely the voltage across this one, this whole branch, not just this side, the voltage across all this. Let me clear this up. So now we are comparing. What we are using right now is this. Right? So this one is 10 volts. So the voltage across this whole branch here, because they are in parallel, is what? 10. But then our interest is this side. So basically, when the voltage gets here, there will be a voltage drop at this side, and then the rest of the voltage will come to this one. So it's being shared, right? So that's what happened. So let's see. If we are doing a voltage sharing, right? Voltage division, this will happen. We are sharing it between this 3 and then this 3 here. So we have a basically, if we are looking for this, we use the other one as the numerator, which is 3, and then at the bottom we add them up, this and then this, right? So we get 3 plus 3, and then the voltage that we are sharing is the 10, right? So you see, very straightforward for this one. So we end up getting the same 5 volts when we use the voltage division. Right? So the voltage across this 6 ohms resistor here, let's go back to the original circuit. Okay, so the voltage across this one right here, this V naught that we are looking for, will be 5 volts. Yeah, so that's all right.